In an unprecedented feat in the history of space exploration, China has just confirmed the success of a mission that seemed impossible. A robotic probe has landed on the mysterious 3I/Atlas, an interstellar object that crossed our solar system coming from the depths of the cosmos. What began as a bold demonstration of technological capability quickly transformed into something much greater. The first samples collected from the surface of this cosmic visitor revealed characteristics so extraordinary that scientists around the world are revising their fundamental theories about the nature of interstellar objects. The mission represented a giant leap both in terms of engineering and scientific ambition. Intercepting a celestial body traveling at astronomical speeds through interstellar space would already be challenging enough, but achieving a controlled landing on its irregular and constantly rotating surface raised the difficulty level to stratospheric heights. The Chinese team developed extremely sophisticated autonomous navigation algorithms capable of calculating trajectories in real time and compensating for the unexpected gravitational perturbations that the object exerted. The tight schedule made everything even riskier. The window of opportunity for the encounter was measured in weeks, not in months or years as occurs in conventional missions. The landing maneuver itself defied all established protocols. Unlike traditional asteroids or comets from the solar system, 3I/Atlas presented an incredibly unstable surface, with material ejections occurring unpredictably. The probe sensors detected sudden variations in surface density, areas that appeared solid but behaved almost like fluids when subjected to more detailed analyses. The anchoring system had to be activated multiple times before finally managing to fix the probe in a relatively stable region. Images transmitted during the descent showed an alien landscape like no other ever documented, with formations that defied known categories of planetary geology. The risk was not merely scientific and technical. The mission carried considerable political weight at a time of intense space competition among major powers. China's success in reaching an interstellar object before any other nation established a new milestone in the space race of the 21st century. Space agencies around the world observed each stage with a mixture of admiration and strategic concern. The operation's success demonstrated technological capabilities that many analysts judged to be still decades away, altering geopolitical calculations about deep space dominance and access to unique cosmic resources. When the first data began to arrive, the scientific team immediately realized that something was wrong, or rather, extraordinarily different. The initial spectrometric readings did not correspond to any known pattern of asteroids, comets, or any other previously studied celestial body. The instruments detected anomalies across multiple bands of the electromagnetic spectrum, from infrared to much shorter wavelengths. Surface temperature varied inexplicably between different regions separated by only a few meters, creating thermal gradients that made no sense in light of conventional theories of heat transfer in space. The structures observed on the surface defied simple explanations. There were patterns suggesting stratification, as if the object had a complex geological history, but the layers did not follow the orientation expected from gravity or known accretion processes. Some formations presented geometries that bordered on regular, with angles and proportions that seemed too deliberate to be the result of random natural processes. Of course, the team maintained rigorous scientific skepticism, but the strangeness of the observations was undeniable. Craters that should be circular presented consistent asymmetric deformations, as if they had been subjected to very specific directional forces. The evidence accumulated pointing to 3I/Atlas being much more complex than any theoretical model had predicted. The object's density varied dramatically between different regions, suggesting a heterogeneous internal structure impossible to form through traditional mechanisms of material aggregation in interstellar space. Localized magnetic fields were detected at specific points, something completely unexpected for a body of this type. And perhaps most intriguing, there were weak but persistent signs of emissions at frequencies that could not be explained solely by thermal radiation or reflection of sunlight. The collection of physical samples was planned with surgical meticulousness. The probe used a specialized drill to penetrate beyond the surface layer altered by cosmic radiation, reaching more pristine material in natural cavities that extended into the object's interior. The process was not simple. Drilling encountered unexpected resistances at certain depths, while at others the material yielded with surprising ease. It was necessary to adjust operating parameters several times, something that engineers on Earth had not anticipated even in the most pessimistic scenarios of their simulations. The collected material presented textures that left planetary material specialists genuinely perplexed. Some samples were granular like lunar regolith, but with a grain-sized distribution that did not follow the normal statistical laws of impact fragmentation. Other portions had almost crystalline characteristics, with ordered structures at microscopic scales that suggested very specific and controlled formation conditions. There were also inclusions of distinct materials, as if different types of matter had been mixed in some process not yet understood. The chemical composition of the samples forced researchers to repeat analyses multiple times, simply because the initial results seemed impossible. The isotopic proportions of common elements like carbon, oxygen, and silicon did not correspond to any known signature from the solar system or even theoretical expectations for typical interstellar matter. There were anomalous abundances of certain rare isotopes that are normally only produced in very specific stellar environments, and the simultaneous presence of these markers created a cosmochemical puzzle of epic proportions. The revelation that truly shocked the entire scientific community came from the detailed chemical analysis of a specific sample collected from a deep cavity. The mass spectrometers aboard the probe detected a molecular signature that no one had ever imagined finding in a natural interstellar object. Complex organic compounds in concentrations and configurations that suggested extremely sophisticated synthesis processes. These were not just the simple amino acids and basic organic molecules that have already been found in meteorites, but intricate molecular structures with specific chirality and bonding patterns that pointed to highly selective formation mechanisms. Even more impressive, some of these organic molecules were organized into structures resembling membranes or matrices, as if there were some type of chemical compartmentalization occurring. The team found evidence of catalytic reactions that could have occurred in the object's past, leaving characteristic mineral traces. The presence of certain clay minerals with known catalytic properties, associated with reservoirs of organic molecules, raised profound questions about the possibility of prebiotic or even biochemical processes having occurred at some point in this interstellar visitor's history. Possible explanations for the exotic origin of these characteristics cover a broad spectrum of hypotheses, some more conservative and others truly revolutionary. The most cautious interpretation suggests that 3I/Atlas may have formed in a very particular interstellar environment, perhaps on the periphery of a dense molecular nebula where unusual chemical conditions prevailed. Under this view, the object would be a natural product of rare but not fundamentally different cosmic processes from known ones. A bolder interpretation proposes that the object could have originated in a very ancient planetary system around an already extinct star, carrying with it chemical vestiges of complex planetary environments and evolutionary processes that occurred billions of years ago. There are also more speculative theories circulating in reserved discussions among some researchers. Some point out that certain characteristics of the samples are difficult to reconcile with any known natural process, even considering exotic environments. The regular geometries observed on the surface, combined with the unusual chemical signatures, have led a vocal minority of scientists to suggest that at least some parts of 3I/Atlas might not be completely natural. This possibility, although treated with extreme skepticism by most experts, cannot be completely ruled out without much more in-depth analyses. What still cannot be officially disclosed includes results of specific analyses that are undergoing rigorous independent verification processes. There are rumors in the scientific community about even more surprising detections awaiting confirmation by different instruments and independent teams before being made public. The exact nature of these possible additional discoveries remains under temporary secrecy, but sources close to the project suggest that the data may have even deeper implications for our understanding not only of interstellar objects but of the very distribution of chemical complexity in the cosmos. The scientific impact of the discovery is already reverberating through multiple disciplines. Astrochemists are revising models about the synthesis of complex molecules in space environments. Planetologists are questioning fundamental assumptions about the homogeneity of small celestial body formation processes. Astrobiologists see in the discoveries an indication that prebiotic chemistry may be more common and diversified in the universe than previously thought, potentially occurring in contexts far beyond rocky planets' inhabitable zones. Established theories about interstellar objects, built largely from the limited observations of Oumuamua and interstellar comet 2I/Borisov, now need to be dramatically expanded. It was implicit in most theoretical models that interstellar visitors would be basically similar to bodies in our own solar system, just with origins in other stellar systems. The characteristics of 3I/Atlas suggest that interstellar space may host a much greater diversity of objects, some with extraordinarily complex evolutionary histories. This has implications for everything from understanding the distribution of material in the interstellar medium to estimates about the frequency of complex chemical environments in the galaxy. Disputes among international teams to validate the data have intensified since the initial announcement of results. The extraordinary nature of the claims demands equally extraordinary standards of proof. Scientists in other countries are requesting access to raw analysis data, something that involves not only scientific but also political and national security considerations. Some nations have expressed interest in launching their own verification missions, although 3I/Atlas's trajectory means it will already be too distant to be reached with current technologies, unless ultra-fast probes with advanced propulsion are employed. The international scientific community is divided between enthusiasm for the discoveries and the necessary methodological caution. Editorial boards of prestigious scientific journals are accelerating peer review processes for articles related to the mission, recognizing the historic importance of the results. At the same time, there is a coordinated effort to ensure that scientific rigor is not sacrificed for the rush to publish. Emergency conferences have been organized, bringing together experts from different fields to discuss implications and plan complementary studies. The possibility of new missions arises as a natural consequence of these revolutionary discoveries. Space agencies around the world are already in preliminary discussions about international collaborations to develop rapid interception capabilities for interstellar objects. The experience with 3I/Atlas has demonstrated that such missions are technically viable, although extremely challenging. There are proposals to establish a denser surveillance network capable of detecting interstellar visitors with greater advance notice, providing sufficient time to plan and launch interception missions. Some of these future missions could include much more advanced in situ analysis capabilities and even sample return to Earth. Bringing interstellar material to terrestrial laboratories would allow studies with much more sophisticated instrumentation than any robotic probe can carry. This would represent a leap comparable to the Apollo missions that brought lunar rocks, opening a new era of planetary science. The cost and technical complexity of such missions are substantial, but the potential scientific value is convincing mission planners that the investment would be justified. There are also discussions about more ambitious long-term missions that could not only intercept but effectively follow interstellar objects on their journeys through the galaxy. Using advanced propulsion, potentially including solar sails or even nuclear propulsion, probes could accompany these visitors for years or decades, documenting changes as they traverse different interstellar environments. Such missions would provide invaluable data about the nature of the interstellar medium and the processes affecting objects during their travels between stars. The upcoming high-precision laboratory analyses awaited include even more refined isotopic studies using ultra-high-resolution mass spectrometry techniques. These studies will be able to identify signatures of specific nuclear processes that occurred in the progenitor star or stars of the elements found in 3I/Atlas. Radiometric dating using multiple isotope systems will be able to reveal the absolute age of the material and potentially identify different generations of formation processes. Detailed crystallographic analyses of mineral phases can reveal the temperature and pressure conditions under which they formed, providing clues about the object's original environment. Studies of complex organic molecules are only beginning. Chromatography techniques coupled with ultra-high-resolution mass spectrometry will allow identification of specific molecular structures and determination of their chirality with precision. The distribution of isomers and the presence of possible organic polymers will be meticulously investigated. There is particular interest in searching for molecular signatures that might indicate organized catalytic processes or even precursors to self-replicating chemical systems, although such a discovery remains highly speculative at this point. The signals that may indicate the true nature of 3I/Atlas continue to be the subject of intense debate. Each new analysis seems to add both answers and new questions to the puzzle. The hypothesis that the object is simply an exotic fragment from a distant and ancient planetary system gains strength with some evidence but is challenged by others. The possibility that unique interstellar processes, not yet fully understood, have sculpted its unusual characteristics remains on the table. And the most radical interpretations, although treated with healthy skepticism, have not been definitively refuted. One of the most intriguing questions remains without definitive answer. Are we observing a product of extraordinary but fundamentally understandable natural processes within known physics and chemistry, or does 3I/Atlas represent something truly new, perhaps indicating phenomena or processes we have not yet catalogued in our understanding of the cosmos? The answer to this question may have profound implications not only for astronomy and planetology, but for our understanding of how common organized complexity is in the universe. As more data is analyzed and new instruments are brought in to study the samples, the global scientific community remains in a state of cautious expectation. The consensus is that regardless of the final interpretation, the discoveries from 3I/Atlas have already fundamentally changed our perspective on interstellar visitors and the diversity of objects that may exist in the galaxy. The Chinese mission not only achieved an impressive technological milestone, but opened a window into aspects of the cosmos that remain deeply mysterious. For those following developments in space exploration and astronomy, this is definitely a moment to pay attention. The release of complete analysis results, when it finally occurs after passing through all rigorous scientific verification processes, promises to be one of the most significant announcements in astrophysics and planetary science in decades. Space agencies around the world have already signaled that they will be publishing their own independent analyses of the shared data, and research institutions are preparing special symposia dedicated exclusively to the mission's implications. What began as a bold demonstration of technological capability has transformed into something much larger, a discovery that may redefine our understanding of the nature and origin of objects that wander between the stars. The samples collected from 3I/Atlas hold secrets about cosmic environments and processes that we are only beginning to glimpse. As more in-depth analyses proceed in the coming months and years, we can expect additional revelations that will continue to surprise and challenge our theories about the universe. Following developments in this extraordinary story means being present at a potentially transformative moment for space science. The international results that will be released in the coming months may answer some of the most fundamental questions about the nature of interstellar objects and, perhaps, about the distribution of chemical and even biological complexity in the galaxy. This is one of those rare moments in the history of science where the extraordinary ceases to be speculation and becomes the object of rigorous empirical investigation.